This is the next video in a series of videos I've been making to help students revise the Unit 1 of the Edexcel GCSE course on forces in motion. So thanks for watching. If you've seen any of the previous videos, I appreciate your support. If you could like, share and subscribe, it really helps the channel do some more work in the future, because we're looking to get up to 1,000 subscribers as soon as possible. That way we actually get monetized by YouTube, and it really will help us make future videos for future students taking exams as well. Okay, so the videos I did before were Newton's first law and second law, balanced forces and unbalanced forces. And then I made a video on Newton's third law, how that affects conservation of momentum, and that really prepares you for A-level. So the next video I'm looking at is today's video, which will be on the link between Newton's second law, momentum, and how you can use that to understand car safety in stopping a car in a safe fashion. Not just a car, but when there are collisions, big forces are involved. How can we design cars to reduce the size of the forces involved? Okay, so revising what is momentum first of all. For those of you who've done the previous videos, that you'll be familiar with momentum as being the mass times velocity of a moving object, and the units are in kilograms and meters per second. So momentum is the multiplication of mass in kilograms by the velocity in meters per second. The page references, as I said before in my previous video, are for students studying the Edexcel GCSE course, and these are the textbook pages with the textbook which goes with that syllabus. Okay, so if you're doing a different syllabus, you'll have to find the relevant chapter in your textbooks. Okay, P should be a small p, M should be a small m, and V should be a small v in this equation, if you're using the symbols. Okay, so this is a slide from the previous video that I made, so I'm going to go straight into the next one. So you do need to know this equation for momentum to be able to understand the rest of this talk. Okay, so change in momentum and force. So if you know Newton's second law as being mass times acceleration, Newton actually didn't put it as mass times acceleration. What he actually said was that force acting on an object is that the object's rate of change of momentum, the force acting on the object is equal to the rate of change of momentum. Okay, that's what I think it should say. In other words, force equals the change of momentum in kilograms meters per second divided by time. Now, if you think about it, change of momentum is mass times the change in velocity. So the change in velocity over time is acceleration. Okay, so it's actually the same equation. So v minus u over t is actually acceleration. So you can take the v, u, and the t, and you actually get acceleration. Okay, so this is another way of looking at Newton's second law, and it says you don't need to learn this equation. Okay, so they mean that they'll give it to you if you're doing the Edexcel GCSE course. However, it is always my recommendation that you learn all the equations, because it shows you understand what you're doing. Okay, the P in the title represents that this is for the Edexcel GCSE students only relevant if you're doing the full physics GCSE course. If you're doing the combined science course, the physics that you're doing in there, this will only come in paper 2, so you will not be expected to answer questions on the rate of change of momentum in the exam. However, they could give you velocity changes, and you've got to be able to work out the acceleration or the deceleration and still use Newton's second law. Okay, so it's not going to do you any harm to listen, yeah? And then when you're revising, make sure you use one of those revision books, the CGP ones, which tells you exactly what you need for paper 1 and exactly what will come only in paper 2. Okay, so here's some questions for you to try. For example, Jack scores from a free kick by kicking a stationary football. That means the initial velocity u is 0, yeah, with a force of 40 newtons, so we know F and we know u. If the ball has a mass of 0.5 kilograms, so we know both m here, and his foot is in contact with the ball for 0.1 seconds, that's the time of the impulse. Yes, force times time is the impulse you give the ball, yeah, as you can work out the change of momentum. Okay, so the change of momentum, mv minus mu, is what they want you to do. You know that mu is 0, so they want you to work out mv. Well, mv will equal the force times the time. So all you've got to do is multiply the force by the time that the contact is made with the ball. 40 times 0.1 will give you the answer of 4.0 kilograms meters per second, or newtons seconds is also a valid unit. I don't think the answer comes up on this slide for some reason. And once you've done that, because you know the mass, you know that the change of momentum will be equal to 4.0 kilograms meters per second. If you divide that by the mass of the ball, which was 0.5 kilograms, you'll be able to work out the velocity that the ball moves away from. Okay, moves away with as his foot lets go of the ball. Okay, so here's some extra questions for you to try. If you want to stop the video and then see if you can get any of these done, you can, or you can come back to them. But I'm going to click, and I think the answers are going to come up next to each question to allow you to work them out. Okay, so I actually use these also with students in A-level as a revision, so this will also be useful for students just starting their A-level course. And the names of the students are 4 of my students for when they were in year 12 and revising Newton's laws. Okay, so there's the answers to 1, question 2, yeah, the answers to question 2, the answers to question 3, and the answers to question 4. I'm not going to go through the questions. This is exam technique that you need to practice using the equation on this page. Ft, yeah, equals mv minus mu, yeah, or you can change it using the triangle depending on your strength algebraically, whether you can change the subject to the equation or not. Okay, if you're continuing with physics up to A level, you should be able to do those problems without any difficulty. Okay, so a bit of problem solving using that. So Newton's second law, change in momentum and force are connected. Okay, so for this, Newton actually said the force acting on an object is equal to that object's rate of change of momentum, and mathematically it's written the way that we just went through. Okay, in other words, the faster you change momentum, either speeding up or slowing down, yeah, I should have put a bracket rather than a comma there, the greater the force involved. Okay, so if you can change your momentum slowly, that means a smaller force is involved. If you suddenly change your momentum, like you bang into a brick wall, of course your momentum will change suddenly, and of course you'll get a big lump on your head because the force will be equally large. So the bigger the time, the smaller the force. The smaller the time, the bigger the force. And this is why I said you can use this method of analyzing forces to talk about safety in collisions. So for example, car accidents or people in cars, why it's safer, for example, to have your airbag as the thing that stops you rather than going through the windscreen. One is softer, one is harder. In the softer object, the time will increase, and in the harder object, the time will be lower, so the force will increase. Hope that makes sense to you. If not, you've got to analyze it mathematically. Okay, so safety features. How do airbags and crumple zones work? Well, crumple zones, the airbags are obviously, we've talked about them, so there's some test dummies in a vehicle that they crash these crash test dummies, they're called. They crash these cars literally into brick walls to see the impact on the crash test dummies when they're testing the safety features of vehicles. So airbags increase the time in which it takes for the object to slow down. And by increasing the time, they will reduce the force involved and save people's lives. Crumple zones are the front of vehicles and the backs of vehicles. They're designed to crumple. Now that crumpling takes time and takes energy, so it actually reduces the forces involved in slowing down the vehicle. Okay? They act a bit like airbags. Of course, the person sitting inside the car is inside what's called the safety cage, and those parts of the vehicle where the passengers are designed not to crumple. So you want the crumple zones to gradually take the energy of the collision by doing work on the material to make it crumple. So basically, in simple terms, the change in momentum is the same with or without an airbag, yeah, and with or without a crumple zone, yeah. But having an airbag increases the time the collision takes to slow you down, and by doing that, it reduces the force in the equation that we did on the earlier slide. Okay, so the same thing happens when you want to stop a car. Two things that a driver must do in order to stop in time. He has to react, yeah, and during his reaction time, the car will travel forward at the speed that it's going at. So you can work out how much distance he travels while he's reacting to, say, an emergency. So what factors can affect your thinking distance or your reaction timing? Okay, so your reaction time, how quick you are to react to an emergency, for example, on the road, will affect how quickly you can stop a car. So, and then once you have thought about stopping the car, your foot will move from the accelerator pedal to the brake pedal, and then you have to consider the factors that affect the braking distance. Okay, so what factors are involved with thinking distance? So in thinking and in braking distance. So for example, if you have any alcohol in you, or you are tired, or you have had some medication, or any type of drugs, it can affect your reaction time, and therefore the time it takes for the car to stop, or the time it takes for you to stop with your foot on the accelerator pedal and move it across to the brake pedal. Of course, things like visibility could also be factors that affect your reaction time. Yeah. For braking distance, obviously wet roads, icy conditions, driving too fast, these are all things that put more difficulty for the brakes to bring the car's kinetic energy down from high to 0. Okay, so slippery roads, either icy or wet roads, can increase the braking distance, and that's how you should say it in the exam. Slippery roads, example, icy or wet roads, can increase the braking distance. Worn out tires and worn out brakes can also increase the braking distance if your brakes aren't working efficiently, or if your tires have a very low level of tread, they will have less friction. Therefore, it's going to be more difficult to bring the car to a stop. And of course, if you're driving too fast, it will also affect how long it takes to decelerate from a high speed to 0, obviously. Okay? So these are all the things that they could ask you about in safety features and safety considerations in bringing a car from a high velocity down to 0. Okay? The total stopping distance is the thinking distance, the distance you're traveling while you're reacting to the emergency, and then the braking distance will then kick in. Okay, so that's an equation you need to know for your exam. These questions are very common in paper 1, so it affects combined science students doing physics, and of course the students doing physics GCSE. It's in the paper that both GCSE students do. Okay, so stopping distance, as you can see, they've shown how the blue arrows get longer. They're the thinking distance traveled. So obviously, if your reaction time is constant, you can see from 20 miles per hour, the blue arrow goes from 6 meters to 40 miles per hour, double speed. It goes double, yeah? And then from 30 to 60, it goes from 9 meters to 18 meters. So the thinking distance increases linearly with your speed of travel. However, you'll notice the red arrows are increasing not linearly, but more as a curve. You can see if you go from 20 to 40, you've doubled your speed, but the braking distance goes up from 6 to 24, which is 4 times. Let's see that from 30 to 60, it was 14 meters, and 60 meters, again, is approximately 4 times, because the energy in a moving car is due to its kinetic energy, which we will study in Unit 4 in EdXL, GCSE, and kinetic energy is equal to half mv squared, where v is the speed. So the speed squared is the energy in a moving object. So obviously, if you double the speed, and energy is directly proportional to speed squared, doubling the speed doesn't just double your energy, it quadruples it, okay? So by quadrupling the energy of motion, that means the brakes have to work 4 times as hard when you have double the speed, okay? That's an important thing to consider. The other thing they didn't put in the slide before, that obviously a bigger, heavier vehicle will also be more difficult to stop than a lighter vehicle. So the mass of the vehicle is also a factor to consider, okay? So when you're answering exam questions on this, they will probably want you to differentiate between factors that affect reaction time and the thinking distance traveled while you're reacting, and you have to be very clear in your communication when they say to discuss the different factors. They want you to be clear in the way that I explained to you. For example, you don't just say the condition of the brakes affects the braking distance. You should say worn out brakes will increase the braking distance. So you don't leave it to the imagination of the examiner to consider whether he thinks you know what you're talking about or you've just got a very general answer. Be very specific in the way you communicate to get the marks. So this is a useful chart. And here is the kind of question they'll give you. They'll give you a velocity time graph. The reaction time is shown, is the distance you travel while you're reacting. Your speed does not, your velocity does not decrease. So the distance you travel, remember, for a velocity time graph is the area under the graph. So it's the area of the rectangle, okay? So if they give you numbers here, yeah, let's say this is 10, 20, 30, 40, 50. If that's 50 meters per second, each square is equal to 10, and this one, each one is 1 second, then you multiply this velocity by the time taken to react, and that will give you the distance traveled while you're reacting. Whereas the braking distance, obviously the brakes come into action here after you've reacted, and then it takes, say, 1, 2, 3, 4, 5, 6 seconds for the brakes to reduce the velocity from up here, say it was 50, down to 0. Now the area underneath the braking for the braking distance is the area of a triangle. So you've got to remember what the area of a triangle is. It's half the base times the height. Yeah? So that's something that we did when we were talking about motion graphs. So this is an application of motion graphs in safety of stopping a car. Okay? I hope that's you found that useful. So this is useful for combined science as well as for physics GCSE students, okay? So remember again, stopping distance is all the area under the graph, and be careful in the exams. They might ask you to work out one or the other or both or the total, and you've got to make sure you've read the question carefully, because I notice a lot of students think they're answering the question. They may have asked for the braking distance and the students talking about reaction timing. Okay, so for students doing the edXLI GCSE, if you're doing the double science, you need to look at question 6 on pages 38 to 39 in your textbook to test yourself before you do your topic test. And for students doing physics IGCSE, you also need to look at moments and momentum and collisions, and we did that in a previous video, and there's additional questions to do on page 47. Okay, well, thanks for watching, and don't forget to like, as I asked you before at the beginning of the video, share it with your friends. I want to get up to 1,000 subscribers with your help as soon as possible. Thank you very much, and hopefully see you in the next video. Bye for now.